Hi guys, how you doing? Hope you're all well. So in this video we'll be covering MOSFETs. They're a class of transistors. You all kind of know the standard BJT transistors, which are these ones, the emitter, base, collector, right? MOSFETs are just another version of transistors. You got over here the drain, gate, source. So they're MOSFETs, field effect transistors. Just a different type basically. In terms of what they look like this. So here's these MOSFETs that I got off of Amazon. They're just like these ICs with like the built-in heatsink. So this is it here. So the only thing that you need to know when it comes to like looking at these is that make sure you read the name on them, because I do have, for example, voltage regulators which are not MOSFETs and they look exactly the same. So yeah, you just got to keep that in mind. They look the same, just read the label basically. It's just like the normal ICs. So in this video we've got two circuits. I've got one MOSFET circuit here where I'm controlling an LED. I'm using the MOSFET to switch on and off the LED, and I'm controlling the brightness of the LED by controlling the voltage at the gate of the transistor, of the MOSFET, which I'll explain in a bit. But yeah, so this is the first circuit that we're going to go over, and the second circuit, if I turn it on here, I've got a motor that's running here. And what's happening is that I'm supplying a PWM signal, a bit loud. I'm supplying a PWM signal, as you can see here on the oscilloscope, via my Arduino to the MOSFET, and then that's then driving this motor. It's all pretty cool. Okay, so what I think is that because BJTs are so popular, and without a doubt, if you're watching this video, you've probably definitely dealt with BJTs, which is just the normal transistors. I think it's useful to contrast and compare the MOSFETs to the BJTs. So that's what I'm going to do in the beginning part of this video. So you got the BJTs here, and then you got the MOSFET. Let me put this down. Okay. So don't get too caught up on the names. It depends on whether it's an N channel or P channel, but don't worry about any of that. The thing to know is that just like normal transistors, the BJTs, MOSFETs, they control the current that's flowing between their two pins. So current that's flowing this way or the other way, they're controlling the current that's flowing this way via the voltage at this gate. Just like the BJT, whereby it's controlling the current through it via the current at the base, I base. So some of the obvious things you can see is that they have different names. Where you've got the emitter on the MOSFET, it's called the drain. Where you've got the base on the BJT, on the MOSFET, it's called the gate. Where you've got the collector, it's the source. Okay, so you might be thinking, then what's the difference? Generally speaking, these MOSFETs are going to be used for high-powered applications. So high-powered applications. So usually, just generally speaking, on a circuit, if you're switching a small amount of current, then you're going to use a BJT. If you're switching a large amount of current, then you're going to use a MOSFET. Also important to note that MOSFETs are more expensive than BJTs. So again, keep that in mind. They cost a bit more dollars, or in this instance, pounds, right? Okay, so when deciding what to cover in my videos, it's always a little bit tricky. I find it a bit difficult because there's just so much information out there. But one thing that I've seen useful when it comes to discussing things when I've been researching MOSFETs is the relationship between the gate voltage and the drain plus source resistance. Okay, so what does that mean? So the gate voltage is this voltage here, right? Voltage at the gate. Now the drain plus source resistance is the resistance R here across here. So this whole resistance here and the voltage at the gate. So what we're talking about here is that what is the relationship between how does this voltage at the gate of the MOSFET affect the resistance of the whole device? So what you want to know is that whilst the MOSFET is off, so whilst this is off, there's no current flowing through it, it has a very high resistance. So MOSFET off equals high resistance. So we assume that it's so high that there's no current flow through the device. Then when we apply a voltage, and this voltage here is increasing at the gate, the MOSFET will eventually turn on, and then whilst it's on, so MOSFET is on, meaning that it's conducting, we assume a very low resistance. For example, like 1 ohm. Now here's the important part, and what we're going to see when it comes to, as you can see on this circuit here. I'll explain this a bit later in the video, but if I take this circuit here now, and then as I increase the voltage at the gate, then what's happening is that the resistance of the device is falling. It's dropping lower and lower, and so my LED is getting brighter and brighter. So that's why I'm discussing the relationship here. So they're inversely related. You want to know that as the voltage at the gate, as it increases, then the resistance of the device decreases, and vice versa. So as the voltage at the gate goes lower, then the resistance of the device goes higher, and we can use that to our advantage. Okay, so I'm going to explain two classes of MOSFETs. We're going to go, let's do two types of MOSFETs, because when you're looking to buy them, which it took me a good couple of hours to be able to buy my first MOSFETs, you want to know the different types, and the type that I'm using in this video is called enhancement. And so the thing to know about these is these are the most common types. So most common, they operate very similar to BJTs. So if there's no voltage at the gate of the MOSFET, then the MOSFET won't conduct electricity. So no voltage at gate equals no conduction. The second type, which you might see, which I don't know too much about right now, but I might end up using it, I don't know, I don't think I'll end up using these, but you never know, is the depletion mode MOSFETs. So these are depletion, I could probably write that a bit better, depletion, it's the best I'm going to do, forgive me. So these work in the opposite way to the enhancement mode ones. So for these ones, you've got the 3-terminal device MOSFET. These MOSFETs will actually allow current to flow through them whilst there is no voltage at the gate. I put base there, I'm so used to transistors. Gate, VG at the gate. So when VG, the voltage at the gate, is equal to 0, then the MOSFET is on. So this is actually proportional. So as we increase VG, I can't spell today. As we increase VG, the resistance of the device also goes up as well. Therefore, the conduction goes down. So as you apply more and more voltage to the gate of the MOSFET, then the resistance of the whole device is going to go up. Therefore, less current is going to flow, until eventually at one point it reaches off and turns off. A high voltage at the gate, and VG is a high voltage, then the MOSFET is off. Okay, so that covers enhancement mode MOSFETs and depletion mode MOSFETs. The only other thing you want to know about, which applies to all types of MOSFETs, is usually they have a standard MOSFET, which usually, for example, you would turn on the MOSFET at 10 volts, for example, and then what you have is the other type called logic level. So these logic level MOSFETs, as the name implies, they are turned on by applying a lower level. Normally, I don't know if you've seen those logic level charts, usually those low level voltages basically, which would be used in things like CMOS. So for example, with an Arduino, it can output 5 volts, while with an ESP8266, I believe it's like 3.3 volts or something like that. So if you got a logic level MOSFET, it can turn on, for example, as low as 1 to 2 volts, whilst the standard one will turn on, for example, 5 to 10 volts. So for the standard one, it may not actually turn on using an Arduino. I did find that with my one, it kind of did turn on, but I'm guessing, it's kind of at the limit there. Whilst if you use a logic level type MOSFET, and I'll show you how to spot the difference. These two, if you get the same MOSFET, they basically have the exact same name. They use the same naming convention. It's just one letter difference. They add an L in there to show you that it's a logic level MOSFET as opposed to a standard one. So you might ask, why use a normal MOSFET if logic level MOSFETs are available? And I think that was my initial question as soon as I found out about, okay, why is there a difference? What's the point? After doing some reading, I found out that because logic level MOSFETs turn on and off at such a low voltage, they take longer than standard MOSFETs to turn off. So if you imagine that, if you're switching at 10 volts or something, your circuit has to drop all the way down to below 1 volt to be able to turn off a MOSFET, whilst over here you could turn off at 8 volts, 7 volts, 6 volts, 5 volts. Anyway, so basically they each have their own use cases, so it's good to familiarize yourself, I think, with all 3 types. I'm planning on doing like an additional video on depletion mode, but in this video we're just going to stick to enhancement mode MOSFETs. So I'm pretty much ready to jump into the actual circuits now. The only other thing that I found which was important is that these MOSFETs actually have a capacitance. So in some way they actually have like an internal capacitor, and so capacitance is, you know, the ability to store an electric charge in a device. So the MOSFET, it can actually store electric charge, you know, like a tiny battery. So the gate terminal in the MOSFET, where you've got the drain, the source and the gate, this gate terminal, it's isolated from the rest of the device using like they call it oxide film layers, oxide film. So it's isolated from the rest of the device, and this layer of film, it actually acts like a capacitor. If you think about, you know, a capacitor like this, and then you get the build up of charges on either side, right? Like this and like this. So that happens here with this device as well, because of there's that separation. Why am I telling you this? The reason being is that MOSFETs cannot be used to switch rapidly between states unless you're using a high amount of current because of this capacitance. And usually you'll see that in a lot of circuits involving MOSFETs, they add a flyback diode because this capacitance can cause problems. Okay, so let's move on to the physical world now, leave alone with this boring theory stuff. So if you see here, I've got two ICs. Let's see if you can see their names. We've got IRLZ34N and IRFZ44N. So this one here, the IRFZ44N, is a very standard MOSFET. It turns on, it's one of those enhancement mode ones. It's an N-channel MOSFET, which don't worry about what that means, but N-channel and P-channel, you need to use them differently basically. So here with this IRF one, the voltage at the gate in order to turn the MOSFET on should be around 10 volts. It will reliably turn on at 10 volts, but you can get it to turn on with less, which I'll show you in a minute. So what we can actually do is, I actually have the data sheet, so let's pull that up. We can actually just Google the name of the MOSFET, IRFZ44N, and then we can find out what voltage do we need at the gate here in order to reliably turn on this MOSFET and have current flow from the drain to the source. We've got IRFZ44N, and then skip the ads. Here we go, Infineon. I should have just typed in datasheet. So here's the datasheet, and then on the second page, it's here. We've got gate threshold voltage, and so here it says the minimum voltage that we need at the gate here on this MOSFET. I keep going to call it a transistor because that's when I see this package, I see transistor in my head, even though it is a transistor, but obviously we call it a MOSFET. So the voltage that we need at this gate here needs to be at a minimum 2 volts, but it won't reliably turn on at 2 volts. However, it will reliably turn on at 4 volts, which is the max there. So that's not the max voltage that you can apply to the gate. You can apply more than that. However, it will reliably turn on at 4 volts, but the minimum you can probably get it to turn on at is 2 volts, and I found that to be the case. You know, I can even get it to turn on like around 1.8 volts. So yeah, it works fine. So let's go to the second MOSFET which I showed you. It's the exact same basically, but it's different by 2 letters. So you got the IRFZ44N, and then you got the IRLZ34N. So this 3 has to do with the current of the how much current it can handle. So if I show you on here, I actually screenshotted it. So I've got the first page of the datasheet for the IRLZ34N, which is this second one here that I'm showing you now. And if we look here, highlighted, it's got continuous drain current 30 amps. So it can deal with 30 amps of current, versus the IRLZ44N, which has a continuous drain current of 47 amps. So this 44 here means that it can carry more current than the 34. So one can carry 30 amps, the other one can carry 40 amps. So that's the difference there between these two. And then we also have the IRF versus IRL. So remember I spoke about the standard MOSFET versus the logic ones. We've got the standard versus the logic level. So this L here means that it's a logic level MOSFET. So that means that it will turn on at a lower voltage. So let's Google this and then pull up this data sheet, and then we'll check what the threshold voltage. Remember, the standard one was turning on at between 2 to 4 volts. Okay, so let's just Google it and check what this one turns on at. So we got IRLZ44N. I made a mistake. It should be IRLZ34N. IRLZ34N. Basically, there are 44N ones, but I couldn't find them on Amazon for Prime, so I just went with the 34 because I knew that I'm not going to be pumping 30 amps of current or 40 amps of current, so it'd be fine. Cool, here's a data sheet, and then now if we go to the second page, we've got gate threshold voltage, and as you can see there, between 1 and 2 volts, so half that of a standard one, so 1 to 2 volts in order to turn on this one. What that means is that when it comes to using an Arduino and we're outputting, you know, let's say 3 volts or 4 volts, we can probably turn on the IRF using an Arduino, but we can definitely turn on the IRL. And so, for example, if you had a Pico project and you wanted the Raspberry Pi Pico, which is a tiny Raspberry Pi, you know, single board computer, to turn on a MOSFET, you would use these logic level ones. So whenever you're using an Arduino or whatever else you're using, use these IRL ones, the logic ones. Just get any logic level MOSFET and that will do the job. Alright, so proper fun now. iPad's going away, no more writing down. Forgive me, I lied a bit. I'm still gonna use the iPad. It's a bit helpful. I figured I was printing stuff out, you know, to write on in my previous videos, and it's way more convenient. The iPad's a little bit awkward, but the thing is, saving paper, you know, I'm trying to get into renewable energy, you know, I don't know. But I suppose I need to charge the iPad, so is the iPad, that's an interesting question. Is the iPad actually cleaner than writing on paper? I wonder. Anyways, so we've got this circuit here. I don't have 12 volts. What I do is I actually am using 1.56 volts. It's a very, very simple circuit. As you can see, I've got a MOSFET, I've got a potentiometer, an LED, and a resistor. Resistor's just for the LED, right? So it's basically a 3 or 4 component circuit here with my VCC. So you want to just know that we've got our drain up here. That's right, drain, source, and gate. So I've got my VCC coming down into the drain of my MOSFET, which is what you can see here, down into here, and then from the source of the MOSFET I've got a 330 ohm resistor, then my LED going to ground. So basically this is my circuit, right? It's just simple enough. This MOSFET here is just acting as a switch. Again, same as the BJT. The only difference here is that this one can handle much more power. So although I'm only driving an LED here, I could drive something much more powerful, basically. Now what I'm doing here with my potentiometer is I'm now dividing up the voltage of my circuit based upon the value that I set this resistor at, and then controlling the voltage at the gate. So if I turn this resistor all the way down to 0, to show you here, potentiometer is at 0 ohms, then what you're going to find is I'm going to have 0 ohms here. So effectively I've just got a short circuit, right? This potentiometer doesn't exist anymore. So I now just have a short circuit just like this. And so by doing that, I've actually just cut off all of this. This whole part is irrelevant. VCC is just going straight down this way to ground, right? And so obviously at 0 ohms, when my potentiometer is at 0 ohms, so if I show you here, I'll turn it to 0. Obviously this whole circuit is just disconnected. My VCC is just going straight to ground. I don't know if this is a good idea for me to short out my battery. Let me just turn it back on. I don't wanna kill my batteries. Yeah, so that's effectively shorted out. Then as I increase, okay, important point to mention is that this point here, the voltage at the gate now, it's going to be 0 volts because there is no voltage drop across here, right? So at the gate here, it's just going to see 0 volts. As I increase the potentiometer to halfway, then let's say, for example, I've got a 1K pot, right? So this would be 500 ohms. So at 500 ohms, what I'm saying there is that half of my supply voltage is going to be dropped across this resistor. So I don't have 12 volts here, I've actually got 6 volts. Now remember, whilst the MOSFET's off, you know, effectively this is a very, very high resistance, and so there's not going to be any current flow here. The current's going to flow this way now to ground. And so what we're getting here at 50% is we're actually spreading my VCC voltage. This point here and this point here are both going to have 50% of my supply voltage. So it's going to be VCC divided by 2 here and VCC divided by 2 here. If I make this, for example, 75%, as I will do here, then here what I'm going to do is I'm going to have VCC times 0.75 and VCC times 0.25. So I'm going to have 75% of my VCC over on this side and 25% of my VCC over on this side. So here I'm going to get 3 volts here and 3 volts here. And here I'll get 7, wait, as if it was, this is actually 6 volts. It's annoying that I didn't change that on my schematic, apologies. So this would be 4.5 volts here, because 75% of 6 volts, and then 1.5 volts here. So what you're going to find here is that for my simulation, my LED was still off at 50%, but then as I increase the resistance, the voltage at the base is also increasing, and then it eventually turns on the LED. The value will be different because it depends on your VCC and also depends on the value of your potentiometer. But at 75% it turns on, and then as I'm going up, so for example to 100%, that means that now VCC is going to be all here, and we're going to have 0 volts here. So here we're going to have my whole VCC, in my case 6 volts at the base. And then so what you're going to get actually, and you can see here from the simulation, is that here my current now flowing through my LED is 6.25 milliamps, but then as I increase the resistance, that increases the current flow through the LED, because remember what I said about the MOSFET resistance as it relates to the voltage at the base. Where did I mention that? Here. Oh no, over here. Okay, there we go. So when the MOSFET is off, it has a very high resistance. When it's on, it has a very low resistance. And then as you're increasing the voltage at the gate, you're also decreasing the resistance of the entire MOSFET. And so as you're decreasing the resistance, you're going to get more current flow, which is what we can see over here. So we've gone from 6.25 milliamps here up to 15.1 milliamps. And so you can see here on my circuit, as I increase the resistance, my LED gets brighter, and as I decrease it, my LED gets dimmer. And so one thing I could do is I could use an Arduino to control and, you know, to put out a pulse width modulated signal, or I could use a 555 timer, as you saw in one of my last videos, whereby I could actually control the resistance of this potentiometer, or just control how much current is being delivered, and then I could dim and brighten an LED. And in this instance here, I'm not actually controlling the resistance of the LED to make it brighter or darker. I'm literally just controlling how much of the VCC is going to the base of my MOSFET. Okay, so this circuit is actually super simple. Let's have some real fun now and introduce some Arduino stuff to it. So here's the next circuit that we're going to do. This is the wiring diagram for it. I've got my Arduino here, over here. And so what this Arduino doing is it's actually outputting a pulse width modulated signal. So I'll show you that on my oscilloscope. Okay, so I ground the Arduino and then tap into over here. Alright, so if I turn on the circuit by connecting ground, then now what you can see is my motor is speeding up, ramping up. When it gets to full, then starts to ramp back down. And so I've got a PWM signal. If I disconnect the motor, what I'm doing is I'm just outputting this PWM signal. Really easy to do from the Arduino. And if you want to do it yourself, I'll show you the code. You are welcome to screenshot this. Here's my code for it. All you got to do is just connect the output pin to pin 6 here. And then all it is literally just 2 for loops, whereby we're increasing and then we're decreasing. And then you have that on an infinite loop, increasing, decreasing. And so all we're doing is just writing an output to our pin 6, and we're starting from 0, and then we're increasing 0, 1, 2, 3, 4, 5, all the way up to 255. So we're steadily increasing our analog write, and then again we're decreasing it and just doing that on a loop. So that's how you would make a PWM signal using your Arduino. Alright, so let's go through the wiring diagram. So what we've got is we have pin, you know, in this instance like pin 13 or something like that, but this is my pin 6 coming to a resistor. So it goes through the resistor, and this resistor is a current limiting resistor, goes to the gate, right? So then this is my PWM signal is coming here into the gate. Now remember, as the voltage is changing at the gate, because it's a PWM signal, so the voltage is increasing and decreasing, increasing and decreasing. So as this is changing, going up or going down, then the resistance of the MOSFET is likewise also As the voltage is increasing, then the resistance is going down. As the voltage is decreasing, then the resistance is going up, which means that it's turning on or it's turning off. And remember, it's not just a solid switch, and that's what's really good about these, is that it's not just a, well, okay, like with a relay, once you reach that voltage, ding, it closes, right? Or it opens. With this, it's like this. As you're increasing the voltage, it's slowly closing until the voltage reaches that point, then it's closed. And then as you decrease the voltage, it doesn't just go dink straight away, it slowly decreases proportionally with the voltage as the voltage is changing, which is really useful because, as you can see, you can ramp up or ramp down the speed of things, as opposed to, you know, for example, if you was using a motor for something, you wouldn't want your motor just shut off unless it was an emergency switch. So here I've got a flyback diode. Don't need to worry too much about this, but when you're dealing with like inductive loads, motors, stuff like that, you want to chuck in this diode across your load. So my load here is my motor, and so you're going to get backward reverse voltage that can mess up your circuit. So stick this diode in this way. Just be careful. I had the diode in the other way around, and my diode was smoking, and I thought something was burning something, but it was me. I had my diode reverse bias, so make sure you have it this way. So I've got my load now across my VCC supply, which for me is 7.2 volts. So from VCC, my 7.2 volts, to my motor, and then into the drain of my MOSFET, and then you got my source just grounded. So it's basically the same circuit as the previous one, as this one. The only difference is now we've got a motor here, and instead of a variable resistor supplying that changing voltage to the gate, we now have an Arduino. So we've got an Arduino here doing this job, and then we've got motor here doing this. And other than that, it's the same circuit. So let's turn it on and show you, kind of give you a little bit of a walkthrough of it. So what I'll do is I'll disconnect my oscilloscope. Cool. So I've got my VCC coming in here, and then this long red wire is my Arduino, and this is where the PWM signal here is coming in. Current limit resistor is going to ground, and then likewise I've got my PWM signal here coming into the gate of the MOSFET here. Then I've got my drain here of the MOSFET coming down here along this wire, and then now into the motor, the negative end of the motor. So same as was on the wiring diagram, my drain to the negative end of the motor. It doesn't really matter with the motor, obviously. And then I've got a flyback diode like this, and so you can see the blocking part is here. So diode is across the motor, and then I've got positive end of the motor, and that's going through, directly connected via this yellow point here to VCC. And lastly, we have our source here going to ground, and that's it. So I really enjoyed this. I mean, I find it absolutely fascinating, to be honest with you. I think it's brilliant that, you know, you can build, really, if you think about like somewhat complicated circuits, when you just have literally just what, three components, just one MOSFET, a resistor, and a diode. And okay, so I can make it look a lot more fancy. You know, instead of using the Arduino to supply the PWM signal, I could instead use a 555 timer. And again, you know, that would just, if I added a 555 timer here, it would make the circuit look super complex. But the 555 timer is simple. If you understand this now, this is simple. Combine them together, and I think that's the reason why I'm trying to do this, because I'm not trying to, I know I could just go on Google and just copy a schematic for a solar charge controller, but I really want to be able to look at a big schematic and go, ah, that's the PWM part, that's this part, that's that part. So what I've got coming up next is I've got to do a video on voltage regulators. So this is a bunch of different voltage regulators. I now know how these work, so I'm going to do a video on it. And then I've also ordered a bunch of different PWM ICs. So like, for example, this TL494, this is a UC3845BN. I mean, yeah. So I've got PWM ICs coming up, which I need to learn about, and likewise voltage regulators. And then I think, you know, if I can start building circuits that include MOSFETs, voltage regulators, PWM ICs, you know, I think we're starting to get somewhere. So I'm excited. If you are, you know, if you enjoyed the video, leave a like. And yeah, I'm gonna keep going, man. I'm loving this. This is brilliant stuff, man. I'm learning a bunch. MOSFETs, you know. One thing I would say as well, I was messing about with some circuits, and I do like to mess about with circuits, you know, off video, because I just want to see what, you know, what I can do really, basically. But I can't do a video on it because if I can't explain it, I don't want to do a video and be like, this is this, and I don't know how this works. So I had a circuit that was doing 4 amps of current, which was scary earlier this afternoon, and my MOSFET was heating up like mad. So I got these on Amazon because I thought, you know, I'll probably need it, and it took me a while to figure out, you know, what these were and what they were called. I know they're heat sinks, but they're like heat sink radiator transistor radiators. It's like £6 on Amazon for 10 of these pieces. Really good. It just kind of like bolts onto there using these screws. So if you're gonna get MOSFETs, I do highly recommend getting these as well, because if you use them for proper circuits, they're probably gonna heat up a bunch. So yeah, keep these in mind as well. Transistor heat sink radiators, something like that. Cool. Thanks for watching, guys. Take care. See you next one. Bye bye.